Okay, so hi everyone. Thanks for being here today. So Julien Bonnel will talk today. He's in US time because he is working at the Woods Hole Oceanographic Institution. So today he'll talk about automatic source localization and environmental inversion for acoustical oceanography. So this session will be, as usual, recorded. So okay, Julien, I leave you the floor. After the talk, of course, you will have some time to discuss and have some questions.
Okay, thank you so much. Thank you so much, Maxime, and thank you so much for the invitation. Thank you, everyone, for attending at that unusual time for you. So it's a pleasure to be back in France remotely and make this presentation. I want to acknowledge right now that nearly exclusively of what I'll be presenting today, I'm not the one who did the real work. The work has been done by 3 students, Marc Goldwater, Ariel Vardy, and Arthur Lam. So we'll see. I'll detail that later. As a starter, I wanted to, acknowledge some things. I know a lot of you are expert in machine learning. That little guy here was me 3 years ago. So that's how I started, with a lot of skepticism. And I have to admit that in a few years, I've changed my mind a lot. And I'm now really happy that, a part of my program deals with machine learning, and I think it's really cool. And it really brings new thing for acoustical oceanography. And I hope, I'll be able to share some of that with you today. So speaking of today, that's the outline of the talk. I'm going to start with some of the context on the associated physics. I do oceanacoustics, so we have to understand the acoustic propagation before we do anything else. Then I'll present you my narrow lens on neural networks for oceanacoustics. We'll see how I intend to use them on why that can be useful in my context. Then if I have time, I'll give you 3 applications. One on marine mammal localization, the other one on geoacoustic inversion. I'll define that term later, and the last one on normal mode propagation. If I ever blabber for too long, Maxime, feel free to tell me that I have to shut up, and I can show 2 out of the 3.
Yeah, it's okay. You have time, I think.
And I don't know how you guys are really running that, but if you've got questions during the talk, feel free to interrupt. I'm pretty sure that if you write in a chat or raise your hand, I will not see it. But I think if that's okay for Maxime, if you just unmute yourself and interrupt.
Yeah, sure. If you want to ask questions, you can, and I will take care of that.
Okay, so here we go. Let's start with the context. So, that cartoon is the context of most of what I do. So I'm interested in, mostly coastal water. That means on the shelf, which, in terms of water depths means more than 10 meters and less than 500, so order of, 50, 100 meter-ish. I'm considering a source or several sources in that talk, exclusively low frequency one. So, in my realm, low frequency means less than a few hundred hertz. If you're a seismologist, that's high frequency, but for us in oceanacoustics, that's low frequency. The range, so the distance between the source and the receiver, we're speaking about kilometers. More than 1, less than 50, something like that. So that gives you an idea of the scale of the problem. And everything I'm going to show today is based on a single hydrophone. And just to give you a better idea of the scale, if you take that cartoon here and you scale it, you respect the water depth to range ratio, you get that blue line here. I don't know if you see it on the slide, on the bottom of the slide. We've got a blue line. So that blue line has the correct water depth to range ratio. So it gives you an idea of the physics we're dealing with. Right? That is clearly a waveguide. So there's no plane wave in a waveguide like that. So we have to take into account the waveguide physics. We have to understand the propagation if we want to do a source localization. So localizing that guy making sounds here, or environmental estimation, which means using the sounds made by that guy, record it further away to have an idea of what's going on, either in a water column or in the seafloor. So I'm going to start with the physics. Yeah, I see your hand. Someone called D. Should I just move on?
Excuse me, yeah, it was me, but just because I can only see part of the slide and not the 100% of the image. So I was wondering if I'm the only one having this problem.
Yeah, I think I saw that on the chat. Other people are having the same troubles, but on my side, it's full screen.
Okay, maybe I'll try just to disconnect and reconnect again. I'm sorry. Go
okay,
on.
no problem.
No, I mean, I can try to make them smaller if that's better. I'll just change screen. No, it's okay on your side, Maxime, you said?
Yeah, it's full screen on my side. I see
okay,
all the slides.
Then I'll move on. So low frequency coastal water, we have to deal with modal propagation. So, you know, for those of you doing signal, actually model the environment as a filter. So the received signal Y in the frequency domain equal the source signal times the impulse response of the environment or the impulse response of your filter. In this specific case, you see that the impulse response of the environment, which the physicians are calling Green's function. First of all, the first thing that you see is that there is a sum indexed by m. So we've got several modes propagating. Each mode is one of those psi m function. They're modal, we call them modal depth function. Their modal function is exactly what's happened on a string. When you have a string and you vibrate it, you've got modes, except that here it's vertically happening in the ocean. And it basically gives the amplitude of the modes, and then the part that propagates horizontally is on the right side of the equation. And if you've done just a little bit of wave physics, you should recognize the cylindrical equation with k sub m, the wave number. And what is important here is that the wave number depends on frequency, which means that different frequencies will travel differently. And traditionally, the modes are studied with vertical line array, which we usually call VLA in that community. And why? It's because when you have a VLA, those psi m guy, they're orthogonal. So you can use the orthogonal probability, you do SVD or whatever you want to actually separate the modes. And usually once you've separated the modes, you won. You can do whatever you want with them, localizing source or estimating the environment. And the question is, what can we do if we've got a single receiver? So one thing we can do is that we can do time frequency analysis. On the right side, you see a spectrogram. I assume most of you are familiar with time frequency analysis, but so we've got, at least when I use it, we've got time running on the horizontal axis, frequency running on the vertical axis. Then the color gives you an idea of the acoustic energy. Red will be a lot of energy, and blue will be not a lot of energy. On what you can see here, you see 5, I don't know, curved shaped bananas, call them how you want. So each one of these guys is a mode. And you can see that for a given mode, if I track that guy in the middle, the low frequency arrives before the high frequency arrives before the low frequency. So that means the propagation speed is frequency dependent. And also, that mode 1 arrives before mode 2, which arrives before mode 3. So that means the propagation speed is also mode dependent. So we've got things that depends both on the frequency, both on the modes. If you're more a signal processor than a physicist, you will say that the received signal is multi-component, and that each component has a nonlinear group delay or a nonlinear instantaneous frequency, if you will. And if you try to make the link between that and the equation that I showed you previously, the position of the mode in the spectrogram, which is the travel time of each mode, is defined by the phase here, so the range times the wave number. On those position, we usually call the dispersion curve. If you are able to estimate the position of the mode in a time frequency domain, you can easily relate that to the range. So you can localize the source, or you can at least estimate the distance between the source and the receiver. Now, the amplitude of the modes, which are the colors along that curve here, from orange to yellowish, they're related to that term here. So they're related to the modal depth function. And you'll see that those modal depth function, they notably depend on the depth of the source. So if you can estimate the amplitude of the modes, you can estimate the depth of the source. And obviously, another thing that's important is that, the modal depth function and the wave number, they both depend on the environment. So you can actually solve a joint inverse problem where you jointly invert for the source parameters and the environmental parameters. Okay. I just wanted to give you two, well, that by the way was a real example. That was an airgun shot. So what they used to do oil and gas exploration, recorded in the Arctic, in I think Bering Sea, by Aaron Todd, a colleague from Scripps. It's probably the nicest modal signal I've ever seen in real life. The things usually are more like that. So on that top spectrogram here is a gunshot by Neurospecific height well. So a gunshot is just an impulsive signal, basically something like that. It's recorded in a Bering Sea. You see, 4 modes. It's as nice as can be as well. That's one of the nicest natural signal I've ever seen. This one, we recorded on the New England mud patch. That's basically 100 kilometers south of Woods Hole, where I'm working, on the New England shelf. And you can see there's a set of red curves. So those are my estimation of the mode position, and you can see a lot of modes. So because of the time frequency resolution, they interfere with each other. So it's not as easy to estimate them, but we've got methods to do that, and I'll cover that briefly later. The key point here is that if you can analyze those spectrograms or those signal in a time frequency domain, you've got information about the source position on the environment that is embedded into the time frequency patterns. And this is something I've been working on for years, and that's not really the topic today. I just want you to know that the information is within the signal. If you ever care, there's a tutorial in Java that you can read that details how we extract the modes with a single sensor and how we use them to solve traditional inverse problem.
Yes, Julien, sorry, I think someone raised hand.
Sure.
You can speak if you want. Or maybe it's just a mistake. I think it's the same person called D. I did not identify previously, but...
Well, it was me, but I didn't raise my hand again. I'm sorry.
Okay, no problem.
I think it's maybe it keeps the previous one. I'm sorry.
Yeah, no problem.
Okay, so I'll just move on, and then I think the take-home message for that first part is that we know that the relevant information is in the signal. We have physics-based signal processing methods to extract that information. I haven't covered that, but you'll have to trust me or go through the literature. And we can do source localization, we can do environmental inversion, we can do joint inverse problem to estimate the two at once with a single receiver. Since people, including me, have been working on that long enough, we understand the limitation, we understand the data information content. We know what we can get, we know what we cannot get. But nothing is fully automated with the traditional methods. So, the relevant data needs to be identified by hand. If you want that one signal of interest that has modal dispersion embedded into it, usually what we do is that, someone has to go through the data by hand, or it's a topographic source and we know where it is. But, there's identifying the data snippet is time consuming. And then none of the processing to estimate the modal information is fully automated. So there's the need for an expert to, sit behind the computer and play with the data for it to work really well. So one of the questions is, hey, can we make that better using machine learning? So that leads us to the second part of the talk. And the second part of the talk is kind of my vision of neural networks for ocean acoustics. And once again, remember that I knew nothing about neural networks a few years ago. So if I say something stupid, interrupt and let me know. The first thing is maybe why are people late in ocean acoustics when dealing with machine learning or AI? And I think the first thing is that if you look at the success of AI for traditional problem like the one driven by Google, image recognition or things like that, you need big data with reliable labels to do your learning. So if we speak about supervised learning, you need those big data sets and you need the labels. If we look at what's going on around us, like Google has billions of cat and dog, and we don't have that. And the self-driving cars, they're maybe they're clever, but they're also working because they've got army of analysts that are manually annotating pictures like this is a green light, this is a red light, and they agree with each other. That's another problem that we have in ocean acoustics. If you've got 3 analysts annotating the data, it's likely that they won't fully agree. Other problems for us is that the environment, the impact of the environment on the noise at sea is severe enough that that impedes reproducibility. Let's imagine you train a neural network to solve an application of interest somewhere, and you try to use that network on data that have been collected somewhere else. It's very likely that it will completely crash down, and that's because the propagation is highly impacted by the oceanography, and the oceanography is changing from one place to the next, and also it's changing this time. Another thing is that the AI community has reference data sets that are used for benchmark, and we are very far from that. So everyone is cooking their own little recipe, and there is no easy way to intercompare the methods that are proposed. So what can we do? We can learn on simulation. Instead of learning on real data, we can learn on simulation, or we can try to supplement propagation models with AI networks. I don't know if we can really call AI. Maybe that's just a computational trick, but it's very likely useful, and we'll see that. It's needed to automate the processes, which I've mentioned earlier, and we can learn from the geoscience community. People have been doing that in the geoscience community for years, and they're way ahead of us. So there's really, you know, an easy step to do, which is copy what they did in another community. We can use AI in specific situations that are AI friendly. For example, if for whatever reason you want to monitor one specific area of interest and you're not trying to, you know, extrapolate to other area, you can probably do that and maybe do anomaly detections. One thing that is important, that's probably natural for you guys, but it's not natural in the ocean acoustic community, is that we have to assess the added value of AI versus the classical methods. We've seen papers where people, you know, redo what's been done with other methods with AI, and they claim it's wonderful, but they haven't compared if it's working as well. One thing that will be important is that, you know, when we do ocean acoustics, going at sea is expensive. So I think we need to rethink the way we do our underwater acoustic experiments to really collect data that are AI friendly, and I'll touch that a bit. And we also have a dire problem with training the new generation. There's not a lot of students doing ocean acoustics in the US, and not a lot of them are doing AI, and we need people that works at the intersection between the two. So I won't touch everything today. I'll show you that we can learn on simulation, that it works if we focus on a specific area of interest, that we can collect data in a better way to do AI, and then we can train people, because most of the work I'm going to present today has been done by students, so they are the new generation. So before that, I'm going to give a brief overview of, you know, how a neural network works and how that can be used for ocean acoustics. So I'm going to focus exclusively on supervised learning. The way I see a neural network for this talk is that it's a black box that can do a nonlinear multidimensional regression. So we've got an input, x, that's a vector. We've got a nonlinear function, f, that is unknown, and we've got an output, y, which is a vector, and y equals f to x. The usual example, if you do you know, image recognition, is that x is an image, y is categories, maybe cats, maybe dogs, maybe something else. And usually you do not have a physical model for f. You cannot write down f, neither by hand nor with a numerical model, but you've got a lot of examples for training. So, you know, you have sets of x sub I, y sub I that are known and that can be used to learn an approximate version of f. So that's how I see a neural network. And now, what about ocean acoustics? So I'm going to use the same picture and see how we can use neural network for that. The first thing that we do in ocean acoustics is that we try to solve the forward problem. So the forward problem is for a vector of environmental parameters that we're going to call x. So, you know, that is maybe water depth, the sound speed in the water column, the sediment in a seafloor. So everything that describes the environment. We pass that through a propagation model that we're going to call f. And this time, that propagation model is known. And we'll get an output, y equal f of x, which is the acoustic field. Or that can be modes or rays or butterflies or whatever, but that's an acoustically quantity. And usually for us, f, that model is known. Either we have analytical equation for super duper easy simple, you know, maybe a plane wave, or we've got numerical models that, you know, you feed them x, they spit y. So that's the usual thing. And, you know, where can we use a neural network here? Well, we can use the existing propagation model to simulate a training data set. So we can make a lot of, you know, input output using our traditional forward models. And then we can train a neural network to learn and approximate the propagations. That takes time, you know, that needs to do that. You need to call the forward model many times, as you will do with a traditional method. But the good thing is that after learning, once you learn that approximate version of the propagation, you can evaluate that faster, and it's much cheaper to evaluate it. So you can use it to solve inverse problem, or you can, you know, put it on board an AUV, so an underwater robot, to do stuff with much less power and much less computation. So that's, you know, one way to use neural network to solve the forward problem. Once again, that has been done in the geoscience community, but barely done in our ocean acoustic community. The other thing is that you may want to solve the inverse problem. So the inverse problem is the same cartoon than earlier, except that we're going to look at it, you know, in the other direction. So we start with an acoustic quantity, say the acoustic field that's been measured on an array at sea. And what we want is that we want to know what are the environmental parameters associated to that. So maybe we want to know the position of the source. Maybe we want to know the nature of the seafloor. So we're trying to go the other way. So we're trying to solve what is called the inverse problem. So in practice, when we solve that use traditional inverse method, which is the traditional inverse problem that everyone does in other community, you want f-1, but that f-1 is unknown. It's unknown on you cannot get it directly. So the solution for a given measured acoustic field is that you're gonna try a lot of environments, and you're gonna simulate the acoustic field that you will get for this environment, and then you're going to compute the match between your simulation and your real data. And you're going to do that for a lot of X, and when you've got a good match, you say, hey, I found my environmental parameter. So that's traditional inverse method. Basically try to, generate the best fit between simulation and your real data. And we can, once again, replace that with a neural network. So you can use the traditional propagation model to do a lot of simulation as usual, but you can then use that to train a neural network to approximate f-1. So you can try to directly learn the inverse problem. On that, once again, to do the training, that costs a lot, computationally speaking, but once the training is done, you can apply that approximated f-1 on as many data sets as you want. So you can do fast and automatic environmental inversion, provided that the training is representative of the experimental condition. And that's one key point, is that when you use the simulations to train neural network, you need to ensure that your real operational conditions are somewhere within your training data set, because nothing tells you that you have extrapolation capacity. And in fact, you mostly don't. Okay, so this is, this was the general background. Now I'm going to focus on 3 applications of those ideas. So work performed by students. I'm going to start with bilingual localization. That work has been performed by Mark Goldwater. Mark is a student in a joint program between UI and MIT. So this is Mark, the first time he went at sea. So he had to go to the safety drill. And he collected data for his PhD, and I'm going to present some of that right now. So the context is that we want to automatically detect and localize dispersed bilingual gunshots. So I mentioned those gunshots in the introduction. Those are impulsive sounds that are generated by, I think, all right words. If they're collected in shallow water, there is modal dispersion, so we can use everything that I presented, but we can train a network to do that for us instead of using the traditional device processing. Working on marine mammal is cool because big data is readily available. In that case, what I'm going to present right now, we got them through a collaboration with NOAA. It's also a good thing because we can demonstrate, our ideas of doing automatic detection and inversion using sources of opportunities, because those right well are making loud, low frequency sound, which can be considered sources of opportunities. So whether you care about the well or don't care about the well, those are still good signals to develop the methods. And it's also important for the bioacoustic community to have automated methods to localize the animals. And I can touch that more later if you're interested in what they do. One big problem when you work with marine mammal is, what about ground truths? You need ground truths to evaluate what you do. And obviously we don't have that with marine mammal. So here in this specific case, what we're going to do is that we're going to compare the performances of the proposed machine learning methods to the performances of the traditional state-of-the-art physics-based signal processing. But I told you the physics-based signal processing requires human labor, so we cannot do a lot. So we're just have, comparison with 50, 100 signal, 50 with just noise and 50 with actual gunshots. One thing that's important, I don't know if I emphasized that enough at the beginning of that slide, is that not only we want to solve the inverse problem, in that case localization, but we also want to do the detection. So we want to feed a long passive acoustic data set, maybe days of data, weeks of data, to a neural network, and we want a neural network to automatically flag the signal of interest and then use them to do the localization. So basically we'll have an input signal that will be fed to our network, or the network will output there is or there is no signal of interest, and if there is one, that's the range of the signal, or the estimated range of the signal. So to do that, one of the tricks that Mark has been using is been training the neural network with a data set that is heterogeneous. So one thing is that he used simulated gunshots that are simulated to many ranges that are simulated in many different environments, so that the networks can learn the diversity of signal that can be encountered in this context, and can also learn how that relates with range, which is the parameter of interest. And you see that here. You see, like, simulated signal for various environment and ranges. But that was not enough to train the detection part of the network. So we also trained the network with actual ambient noise measured at sea, but also what the array processing community will call interferences. So signals, but signals that are not signal of interest. So we fed everything to the neural network so that the neural network can learn what is interesting, the dispersion of the modes and how that relates with range, but also what is not interesting, which are the interferences on the ambient noise of the ocean, which is non-stationary and non-white. The network that Mark has been developed is a temporal convolutional networks. The input data is a spectrogram, which is seen as 1D sequences. There is here an example, an illustration of the building block of the network that he used. He used basically TCM. And we have a composite loss function that does both detection and localization, and we try to weight that clearly. I won't go into the details. I won't be able to speak about it anyway, but obviously we had various performance metrics is the usual one in that case. What is more interesting maybe here is to really speak about the results. So on that first part of the slide, you see the result for simulation, and here is a plot of the estimated range on the vertical axis versus the true range. So, as usual, when you do simulation, everything works, right? So, we've got a detection with accuracy, precision, recall, everything's like 98, 99, something. We've got ranging error. So in an environment that's largely unknown, which is a few hundred meters, which is, pretty good for that kind of application and clearly good enough for what the marine mammal people have to do with this data. And you see here that there is no real bias, or there is no, there is a bit of dispersion, but that's expected because there's noise, and things are working really well. Now, what's usually a trick in ocean acoustic is not the simulation, is what happens when you go to real data. So we've done that, and I told you the problem with the real data is that we have no ground truth. So we apply the network on a lot of data measured in the Bering Sea, and then we got a lot of estimated range, and what can we do with them? So we manually localized some of them, 50 of them, and then we got that plot here on the right. And you see that the machine learning, the automated machine learning method is doing as well, or maybe as bad as the manual physics passing and processing methods. If you want to quantify that a bit more, in terms of accuracy, precision, recall, we're pretty good, 90%, 100%, 80%. So that's aligned with the traditional detection method for marine mammal. On the ranging precision is in the order of a kilometer, which is not too bad in that context. Just for the reminder, so we're feeding a long time series to a network. The network detects the signal of interest. The network doesn't know anything about the environment. All the environmental uncertainty and variability is embedded into the training set, and it flags sources of interest, and it localizes them within a kilometer. One maybe things that we've done that may be interesting for you guys is we've just been looking at a few signal that have been detected and signal that have been missed. And what you can see is that obviously the detected signal are pretty nice and the missed are pretty not nice. And what not nice means in this case, it can mean a low signal to noise ratio, which you can see on the right side, or it can mean a good signal to noise ratio, but not a lot of dispersion. So whether that signal in the middle is dispersed or non-dispersed is probably something an analyst will disagree. So we kind of understand why the network is not working perfectly, and that was to be expected. Okay, that's all I have on the marine mammal side. I'm now going to speak about geoacoustic inversion. So it's the work by another of my students in a joint program here. That student is Ariel Vardy. He's here. So he's been the one leading the charge on that topic. So what is geoacoustic inversion? I don't know if there's anyone in the room who knows what geoacoustic inversion. The idea is that when you do ocean acoustic at sea, you need to know the seafloor geoacoustic parameters to predict acoustic propagation in the water column. Even if you care exclusively about what's going on in the water, you need to know the seafloor, because the seafloor is your boundary condition. So you need to know what's going on here. So whether you're in the Navy and you want to assess your sonar performances, or maybe you're an ecologist and you want to forecast noise pollution, or you want to localize marine mammal, you need to know what's going on in the seafloor. So estimating the seafloor property using acoustical remote sensing method is called geoacoustic inversion. There was a little the stupid cartoon here. On the left was a cartoon of the by the New York Times saying that basically the physics of sand is the most difficult physics that you can work on. And if you put that sand under the sea, it's like animals that borrow water on top. It's even more difficult. And basically what you do is that you've got a ship with the sources somewhere, you've got a receiver somewhere else, and you try to estimate the property of that mess here. So that is geoacoustic inversion. So what the context Ariel has been working in is that is been working in a controlled, man-made experiment at sea, which was called the Seabed Characterization 2022, that took place on the New England mud patch. So that's the piece of seafloor that is muddy on the New England shelf. Which is interesting for sediment acoustic people. I'll spare you the nasty detail, but basically we had a set of receive. I mean, we had a lot of instrumentation, and there I deploy a set of receiver which are flagged TOSIT here. So it's just good enough for you to know that it's just one single hydrophone. So we've got several stations with one single hydrophone. And people in another boat have been deploying explosives, Navy explosives. They're called sus charges everywhere on the mud patch. And here we're just going to be interested in explosives that have been deployed at the center of the mud patch and recorded on all the TOSITs. Within that context, so we've got like 17 TOSITs. The sus charges at the center of the mud patch have been dropped over the course of 2 days. So basically, 2 days of data per sensors, 20 sensors, that's 800 hours of data on a bit less than 300 signal of interest. That we want to use to estimate the environment. So, Ariel's task was to develop a machine learning method to automatically detect the dispersed sus charges and use them to do environmental inversion. One thing that is important is that that experiment took place during spring, and spring is a really interesting time, oceanographically speaking, on the shelf. The water column is highly variable. If you care about physical oceanography, we can discuss that further. But basically, from an acoustical point of view, there's enough fluctuating and dynamic mess in the water column that we cannot assume that we know the water column. So we also have to invert or take into account the fact that we don't know the water column when we try to invert for the seafloor. So Ariel's method is kind of similar to Mark's joint detection on inverse problem. Ariel decided to go with 2 chain neural network instead of 1. So first the detection stage and then an inversion stage. Ariel also decided to work with time series instead of spectrogram, but it doesn't change the overall idea. So the input data is a raw time series. On the final output after 2 chain neural network is source localization, both range and depth, and then seafloor geoacoustic parameters. So to do training, well, same than the idea of Mark. We're going to use a mix of simulated signals on empirical noise. Here, because we care about the environment, it's important to look at the variability of the simulation that we use for training. So we had to deal with the fact that the water column was largely unknown, and that the fact that the sediment was also largely unknown. So that's how we modeled the environment. I'll go through that briefly, but basically he modeled the sound speed profile in the water column with 4 nodes. So we do basically 4 sticks. The first one must be at the surface. The second one must be in the seafloor, at the seafloor. In between, they can be basically anywhere else. Bounds for sound speed in the water column that are reasonable for that place at that time. The seafloor depth is also varying a bit on that place, so we had to give some freedom to that. Then we model the seafloor as a sediment layer over a basement. So the sediment we know is supposed to be mud, but Ariel still used kind of wide bounds for mud parameters around here. So thickness, between 5 and 15 meters, sound speed between 1300 and 1600, density between 1.2 and 2. So if you know anything about sediments, those are relatively wide. Like it's not introducing a lot of prior information. And then the bottom R space, and then also it gave variability to the source, both in terms of range, can be anything between 500 meters and 10 kilometers, and depth between 10 and 30, because we know we're dealing with those charges. We know those guys are supposed to explode around 20 meters, but we give variability to see what the network can do. One thing that Ariel was really wanting to do, and I didn't believe him, Ariel told me there is no need to do a big training data set. The network would be really good at interpolating. I want to do a small training data set. And I told him, I don't care, do a big data set. So we did both. He did a big data set with 4 million, I mean, big for us. So 4 million simulations. And he did a small data set with like less than 200,000 simulation. And boy, he was right and I was wrong. So here is the result. The first thing is that on the detection part, the network detect all the sus charges and made no false alarm. You know, that can sound crazy. It's not. We're trying to detect loud explosive, right? So it's not difficult to detect them. The cool part where the thing is interesting is that, you know, not only the network detected the loud impulses, but it focuses on the one that were dispersed. You know, there were other impulsive, non-dispersed signals, and those did not generated false alarm. So, you know, as you just choose a simple threshold, there would have been false alarm, and the network was able to not flag the potential false alarm as detection. So that we were happy about that. Then I told you, we know where are the sensors, we know where the sus charges have been deployed. So we've got a ground truth for range. So here is the result for the ranging. So you can see predicted range on the y-axis, true range on the horizontal axis. If everything were perfect, we would want to see all those guys on the diagonal. You know, they're on the diagonal. They're not perfectly on the diagonal, but they're enough on the diagonal that we're happy with the result. And one thing that's important here to see is that, you know, with the small data set, you do, with the small training data set, you do as well as with the big training data set. So Ariel was right from the start. The network doesn't need a lot of training example. It can interpolate well enough with a small training data set. So that was a cool result. Then if we look at the inversion result, so those are here on the table on the right, the result for the inversion. The first two columns are the big training data set. The column on the right are the small data set. And, you know, the results are very similar. So once again, that was a cool result that Ariel found. The source depth is 18 point something meter. That's what we know the sus charge should explode at. They should actually explode at 18 meter, or the equivalent of 18 meter in crazy imperial units with a bit of variability. So that's good. Sound speed is found at 1480, so less than 1500. That's what we want. The mud is supposed to be slow, density 1.6. That's consistent with core. There have been, you know, geophysical cores there, and we know that the density is 1.6. And the rest is consistent too. On the bottom plot, you see histograms of the environmental parameters. So since we've got so many sus charges, so many signals, we can do statistics of the result. And if we assume that the environment is homogeneous, we would like to see just, you know, a single spike somewhere. So, you know, whether the environment is fully homogeneous is a question. And I'm going to speak a bit more about that later. But you see that in blue and orange are the big training data set and the small training data set. Once again, it doesn't make a lot of differences. So that's good. And you see that, you know, the source depth is consistently 80 something meter. The sound speed in a mud is consistently slow. The density is consistently 1.6, etc. So that all makes sense. Okay, so that's what I have for inversion. I'll come back to that a bit later for at the conclusion. Before that, I'm going to speak about the work by Arthur Varlon. So Arthur is a French student. He did that work as an engineer, working between Gypsalab and Woodsole with Jérôme Mars. He will start in a month test cifre between Gypsalab and Alcima. So the two previous applications I showed were about inverse prem, and this application is about forward prem. So what Arthur did is that he used a neural network to predict shallow water propagation. So he used a traditional numerical model that is called Kraken to predict the mode wave number on the group speed. And then from there, he used inverse iteration to predict the modal depth function from the wave number. And then he used the predicted modal wave number on the modal depth function to predict the transmission loss, to predict the full acoustic field underwater, which is what most people care. And then we can use the group speed for geoacoustic inversion. What the result I'm showing you there were preliminary results from Arthur. He had an example where he assumed he know the water column really well, but he gives freedom to the sediment, to the seabed, so both the sediment and the basement. He used a simple 4-layer network that we actually discover in the geophysics literature, and basically it's working well. So I won't go into too many details, but the network is able to predict the group speed. It's able to predict the wave number, you know, with really good precision, like the the 95% of the error on the group speed is less than, you know, a percent. So that's pretty cool. Using the prediction of the network for the wave number, we can do usual, you know, acoustic cooking, and we can predict the transmission loss. So that's what the acoustic field look like in a waveguide. Using on the bottom is the truth, on top is the truth, on the bottom is the prediction, and, you know, by eye it's similar. If you do statistics on a lot of iteration, basically we predict the acoustic field, you know, within a dB 85% of the time, or within 3 dB 95% of the time. And what is interesting is that the pattern is really good. Where we do mistake is in a value when it's really low or really high. So the network is able to predict an acoustic field, to predict the interferences at a good place, but the value, the exact value of those interferences may be wrong by a few dB. What is interesting, I think, is that if you use the neural network to predict the modes, and then you use the predicted modes to predict the acoustic field, you've got much better results than if you use the neural network to predict the acoustic field directly. And that's because the neural network acts as a good interpolator. And if you change the environment a bit, you will change the modes a bit, but you will change the acoustic field a lot, because the acoustic field is a sum of modes with cross term. So you know, there is a small change on the environment has a high impact on the acoustic field, but not so much of a high impact on the modes. It's varying slowly, so it's easier to interpolate for the network if you predict the modes rather than predicting the acoustic field directly. I'll spare you that on inversion, and I'm gonna switch to the conclusion. You know, I've convinced at least myself and a few colleagues that machine learning is useful for faster and automatic processing. We can approximate forward propagation models. Here I gave you an example of normal modes, and we can run automated inverse problems like localization and environmental inversion. Everything I presented today was clearly an interesting educational story, both for the students and for me. I learned a lot along the way. You know, maybe that story is good enough for you, but, you know, being in an oceanographic place like Uzo, people ask me, hey, what about, you know, can you learn something about the ocean? They don't care that much about the method, they want to learn stuff about the ocean. So I'm going to try to convince you that we can use this method to learn a few things about the ocean. So going back to the geoacoustic inversion study, people are really interested in learning the spatial variability of the seafloor at the scale of the mud patch. Obviously, you know, you can core. So people have been doing that. You know, people at USGS, they've been coring that place as much as they could. I think they collected like 300 cores on that place, which is like 20 by 10 kilometers. But the cost of that is prohibitive. Here, what we can do is that, you know, using the setup that I presented you with, you know, a distributed array, what's going on. Okay, I forgot to plug my computer, so I'm going to do that right now. Okay. With the setup that I presented you here, with a simple, you know, distributed acoustic array and distributed acoustic source, you can generate a lot of signal to cover the area, and then you can use machine learning to automatically process hundreds or more of inversion results. Ariel is currently analyzing all the source charges collected on all the toast sets on all the receiver deployed at that experiment. So that we're speaking about more than 3,000 acoustic signal, which has never been done before. Before I spoke more about that, I wanted to present you, you know, another way to see the results that I presented earlier. Is that if we pull the results you obtain on the west side of the mud patch, and we pull the results you obtain on the east pattern of the mud patch, we see those two histograms for the sound speed of the mud. And those are statistically different, and they suggest that the sound speed is lower on the west than on the east. And that is fully consistent with results obtained by people who did like in situ grabbing and measuring the acoustic properties of the mud. So I told you we're now looking at more signal on the same place. So we've got, so I got the number wrong on the previous slide, but we've got nearly 5,000 signals. And we can do, you know, kind of the traditional tomographic problem. You know, we've got a lot of tracks that covers the array of interest. For all this track, we've got modal dispersion, and we can solve the geoacoustic inversion problem. So Ariel did that. He limited that study to tracks that were less than 10 kilometers, that he can use the same network. That still give us like more than 3,000 tracks. And those are the results of the sound speed in the sediment layer as a function of latitude and longitude. And you can see, you know, dispersion, but still a significant increase So that suggests that the mud speed increase when you go toward the northeast. Once again, I'll spare you the nasty details, but that is fully consistent with a geological study that has been covering that place a lot. So they've been doing, of course, geological and geophysical models. And what you see on this map, let's just focus on that one, is that the mean grain size of the sediment, well, take that with a grain of salt, in the first 10 centimeters of the mud, basically, goes from decrease when you go from bottom right to top left. And we know that if the mean grain size decreases, the sound speed has to decrease as well. So the results from the neural network are fully consistent with the geological studies. And it's pretty good to see that we've got enough precision to find results that are really interesting for the geophysical community, because knowing that the sound speed decrease suggests that the grain size change, and then they can use that to learn more about the deposition process of the sediment. And also, since we can cover places with that many tracks, we're not too far from doing like 3D mesoscale seafloor tomography. So that's what we're working on right now. On the marine mammal side, what I've been I've been working in the past on localizing marine mammals. For example, that's a paper with Aaron Todd from Scripps, and we did, that was important for the North Pacific Right Whale in the Bering Sea, blah 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 blah. The important thing is here. So a lot of blah blah blah, and then 6 gunshot samples and 3 up-call samples remain. So when you process the data by hand, those are the small numbers you're dealing with. And what we showed is that we estimated the depths of those calls, and the depth distribution of the calling animal was different for these 2 types of call, and that is important biologically speaking. But our sample number were really, really small. And it's important to increase the sample number, particularly, not to on the East Coast. We're studying the North Atlantic right whale. That is a super duper endangered population. There is less than 500 animals left. And so a lot of people are working on them, obviously, we're not the only one. What we've done with Mark and other is that we've deployed what we like to call an acoustic carpet. So those are just single receiver bottomlanders in Cape Cod Bay. And we've been using Mark's neural network to range the animal. But if you can range from a single sensor, that basically gives you a circle. And then if you've got a network of receiver, you can cross the circle and you've got a latent localization of the animal. So we deployed those bottomlanders. I don't know if you can see them well, they're here in Cape Cod Bay. We've got a lot of right whale data, and Mark is, currently working and extending his method to estimate the latent position of the animal on maybe their calling depths too. And here's an example of, localization for one day of data. And that's very important for the people studying as well, knowing where they are, when they arrive in the bay, what they do in the bay. This is important to help protections. Here is just an example of 4 days of data. All the crosses are the acoustic localization. The lines that you see is that they basically fly a plane every day to count the animal. What we see here is that, no surprise, but the acoustic localization on the visual survey give results that are different because the coverage is not the same. It's by mixing the two that in the end we'll be able to learn as much as we can. So conclusion again, I mentioned in the beginning that the physics-based processing give us capacity to extract information from a single receiver. If you combine that with machine learning, you can process big data. With machine learning, you can process big data. And when you put the two together, I don't know if we really do what's called physics-based machine learning, but at least for sure we can develop new methods for acoustic observation of the ocean. What I've been pushing here at Hui is to go from the large, synchronous array that are used in the field. You see an example of what we call the acoustic telescope at Hui, toward developing sparse distributed network of simple sensors. Those are the sensors that we put on a mud patch that we put in Cape Cod Bay. They're just basically bottomlanders. We also develop Argo floats with acoustics, both with the colleague at Hui, also speaking with the colleagues in Build French. And the idea is that in the end you'll have a distributed networks, and if you can do machine learning, then you can process everything to get more information about the ocean. That work was supported by the Office of Naval Research in the US on the Direction Générale de l'Armement in France, so many thanks to them. Nothing would have been possible without their financial support, obviously. I wanted to let you know a bit of advertisement at the end. that we've got tenure track scientist position available at UI, one in sensing, robotic, and machine learning. So that may be interesting for people in your group, one in ocean acoustics and one in applied ocean physics. If you're interested, please send me a message. If you know people that are interested, please tell them to contact me, or I can give you the listing. Or the even more selfish situation, I've got a postdoc position available in my group. The idea is to work on that big experiment that's called the New England Cement Acoustic Experiment. I'm sure no one here knows about the New England Cements. Google Maps know about them. Here they are. So, Uzul is there. That's the New England Cements. They've got a pretty bad review. I don't know who ever reviews Siemens on Google Maps, but they've got a bad review. That's unfair. It's a pretty cool place. It's in the middle of the Atlantic Ocean. So the Gulf Stream is there. So acoustically speaking, we've got a really difficult situation that mixes complex topography, complex physical oceanography. A lot of PI working on that. My little part of that big cake is doing geoacoustic inversion. They're probably using machine learning. So if you're interested, or if you know someone that's interested, please pass the word around. That's what I have. Thank you for your attention. And if we have time for questions, I'll be happy to take them.
Yes, sure. Many thanks, Julien, for this talk. I'm not a specialist in acoustical oceanography, but I learned many things. I think it gave us a nice overview of what happened regarding AI in these fields. So, of course, we have a few minutes for questions, though I leave the floor to the audience. Do you have any questions? I think if you have, you can unmute yourself normally. Well, maybe I can start and let you think if you have additional questions. Maybe you already gave us some answers in your conclusion, but at the end of your introduction, I was wondering, because you were speaking that you used traditional physics-based signal processing traditionally to deal with these data sets. And I was wondering if it would be easy to embed these traditional physics-based methods in neural networks, either in the neural architectures or by constraining the loss as it is done in physics informed neural networks, if you already have some insights on this topic.
My only insight is that we haven't done it yet and we have to do it soon.
Okay.
I think it's a really good question. It's the natural next step.
Okay.
You're right. It's been done in other fields. We started recently.
Okay.
I don't think anyone has done it in our community.
And do you know why? Because is it more difficult than in other fields?
I think it's mostly because as much as I don't know a lot in machine learning in my community, I'm not far from being an expert. Right? Okay. It's been the field has been different enough that people just don't know. People just don't know the state of the art. So we're rediscovering warm water every day. That's what we do.
Yeah, sure.
And it's it's difficult. You have to imagine that the skills of running an experiment at sea and the skill of being an expert in machine learning are really different. Mm-hmm. So it's tough to have people that are knowledgeable in the two, and that's why I think training students is a good thing to do. And students working on that knows more than the PI by now for sure. Yeah,
sure. Okay, thanks. And maybe I had also some maybe more let's say technical question. It's not very technical, but it was in your application. You were, I think, in the first applications on whales. You told us that you were using some composite loss function for both detection and localization. I was just wondering, because we often have the same problem for me in spatial oceanography, try to reconstruct two problems in the same time. And I was wondering if you have a convenient way to build this composite loss function to wait between both aspects you want to reconstruct, or do you it by hand, or do you have a more convenient way to do it?
We started to wait by hand, and I think we learned the weight along the way.
Okay. And learning the weight, it does not, goes in favor of one variable against the other? Or?
It does not seem to be an issue here, but I think it's because our detection problem is so much easier than our localization problem.
Yeah.
That the trade-off between so long that how much the fact that you give a bit more importance or a bit less importance is not that much of a problem. That's my guess.
Okay.
We never investigate that a lot because that has not been a problem for us, to be honest.
Okay. And maybe, yeah, along this line, it's a bit the same questions, but on the second application, you told us that you were using 2 different one-dimensional neural networks.
Yeah.
And I understood that it was, you trained a first neural network and then a second one. First for detection, then for inversion.
Yeah, so we don't
and
have
I was
problems.
wondering, why did you do that? Is it working better than a joint learning of both problems in the same time, or?
It was it was an arbitrary decision on the students.
Okay.
That's the way he wanted to do it. It's been working well enough that we never really question it. In a sense, having the 2 students working in parallel with different way to solve the problems. You could have asked the question, why one is working on spectrogram and what is working on time series. It's because those are things that we try to investigate in parallel. On right now, we do not. It's new enough that we don't have a good answer. Apart from we tried, and it seems not to make a big difference.
Okay, great. Thanks. Is there any other questions in the audience? Okay, if not, it's perfect. It's 4 in France. It's a perfect schedule. Well, I think maybe some of our students maybe could be also interested in contacting you. They are currently working on the acoustical oceanography, even if Roland's team, so I think it could be interesting. If this is okay for you, Julien, I will put the video on the OceanX website. Maybe if you can share the slides also, if you agree.
Yeah, I can share the slide.
Okay, perfect. I will put this by the end of the week so that a lot of people could not attend today, but I will share this to everyone. Okay.
Okay, cool. Thank you so
much.
Thanks
for the very cool talk, Julien. I hope to see you soon. Okay,
bye-bye.
Have a nice day in the US. Bye-bye.